Have you ever stopped to think about what a photo, your favorite song, and a text message actually have in common? I mean, it seems like they're completely different things, right? But deep down, they all speak the same incredibly simple language. So today, we're going to pull back the curtain on the secret world of binary.
Yeah, believe it or not, every single piece of digital information you've ever interacted with is built from just two symbols. That's it. It's the secret alphabet that powers our entire digital world. And today, we're going to crack the code together.
Okay, so when you get right down to it, all a computer really is just a massive collection of billions of tiny little electronic switches. And each of those switches can only be in one of two states, on or off. That's all. And we represent those two states with numbers, 1 for on and 0 for off. And that, right there, is the heart of binary. So this whole method, it has a name. It's called binary representation. It's what we call a base 2 system. And you've got to understand, this is the universal language. Every single modern computer, every smartphone, every digital device on the planet, they all speak binary. All right, so how in the world do we get from a simple on-off switch to, streaming a 4K movie on your TV? Well, it all starts with something pretty basic, learning how to count using just those two symbols. To get our heads around this, let's start with what we already know, right? Our everyday counting system, which is called decimal, or base 10. We use 10 digits, 0 through 9. And each spot, the ones place, the tens place, the hundreds place, is just a power of 10. Well, binary works the exact same way. The only difference is that since it's a base 2 system, it only has two digits, 0 and 1. And each place value is a power of 2. Okay, let's actually look at how this works. If you start from the right, that first spot is the ones place. That's just 2 to the power of 0. The next spot over, that's the twos place, then the fours place, then eights. You see the pattern, right? It just doubles every single time we move one spot to the left. All right, let's put it into practice. How would we read a binary number like 1101? It's actually super simple. You just add up the value for any position that has a 1 in it. So we've got a 1 in the eights place, a 1 in the fours place, we have a 0 in the twos place, so we ignore that, and a 1 in the ones place. Let's add them up. 8 plus 4 plus 1 gives us the decimal number 13. See? Simple as that. Okay, so now we get the digits. Let's look at how they stack up to create, the actual building blocks of data. So each one of those individual binary digits, a single 1 or a single 0, has its own special name. It's called a bit. Think of it as the absolute smallest, most fundamental piece of information a computer can possibly deal with. But here's the thing. A single bit by itself, it can't hold much information, can it? So to represent more complex stuff, we have to group them together. And the standard grouping, the one we use everywhere, is a set of 8 of these bits, which all come together to make one byte. You've heard that word before, right? A byte is our standard unit for pretty much all data. And the reason it became the standard, a little bit of history here, is that a group of 8 bits gives us just enough different combinations to represent a single character, like, say, a letter of the alphabet or a comma. And this is where things get really, really powerful. Look, 1 bit gives you 2 options. Add another, 2 bits give you 4. But by the time you group 8 of them together to make a byte, you suddenly have 256 different combinations you can make. The growth is it's exponential. And this connects directly to stuff you see every day. I mean, have you ever wondered why your phone or your computer has storage that comes in weird-sounding numbers like 64 or 128 or 256 gigabytes? It's not random. It's because the entire system is built on this base 2, power of 2 logic we've been talking about. Okay, great. So we can count positive whole numbers. But what about everything else, right? I mean, how do computers handle negative numbers or numbers with a decimal point? Well, let's start with a bit of a puzzle. If you go into many programming languages and ask a computer to add 0.1 and 0.2, you might not get 0.3. Instead, you get this. A number that is so close, but just a tiny bit off. So what is going on here? Yeah, why does this happen? I mean, we think of computers as being perfectly precise, so why can't they handle what looks like super basic math? Okay, the key thing to get here is that this is an approximation issue, not a bad math issue. Just think about how the fraction 1/3 can't be written perfectly in our normal decimal system, right? It's that repeating 0.333 forever. Well, it turns out a simple number for us, like zero point 0.1, becomes one of those repeating infinite fractions when you try to write it in binary. And since a computer only has a limited number of bits to store it, it has to cut it off somewhere. It just stores a very close approximation. And that tiny leftover bit, that's the error we're seeing.
So, what about negative numbers then? Well, computers don't just stick a minus sign in front of the bits, they use a much more clever trick. Usually, they'll reserve one bit, often the very first one in a byte, to act as a sign bit. If that bit is a 0, the number's positive. If it's a 1, the number's negative. It's a really neat system that lets the computer handle both positive and negative values using the same basic rules.
All right, so we've got numbers covered. That's a huge step. But how do we make the leap from just numbers to representing, well, all of human language?
Well, the first big breakthrough on this was something called ASCII, and it was a simple but absolutely brilliant idea. Just assign a unique number to every character. So, using 7 bits, ASCII created a map of 128 codes for all the uppercase and lowercase English letters, all the numbers 0 through 9, and all the common punctuation marks you'd need.
But ASCII had a really big problem. With only 128 spots available, it was pretty much built for English, and that's it. It had zero room for accented characters, like an E with an accent, or for entire alphabets from other languages like Cyrillic or Greek. And as you can imagine, this led to a massive problem when people from different countries started trying to share information. And that problem actually has a name. It's called mojibake. And I am almost certain you've seen this yourself. You open a file or an email, and instead of text, you just see a bunch of scrambled, nonsensical symbols. That's mojibake. And it's what happens when a computer tries to read text using the wrong character map. So the solution that fixed all this? Unicode. It's a universal standard. And its goal is beautifully simple. Provide one unique number for every single character in every single language on every single platform. No more guessing. And when I say every character, I really mean every character. Unicode has room for the English A, the Cyrillic Ya, the Chinese character for Han, and yes, even the thumbs up emoji. All of them. This is the standard that makes our modern, global, multilingual internet actually work. Okay, let's bring this all home. From a simple on-off switch all the way to a global communication system, it all boils down to one single, powerful, unifying idea. And this is really the key takeaway from all of this. It doesn't matter what you're looking at, a number, a word, a high-definition photo, or an entire operating system. At the end of the day, to the computer, it's all just one thing, a very, very, very long sequence of ones and zeros. I mean, it's an incredibly powerful concept when you think about it. All the amazing complexity of our entire digital world, and it's all built on the simplest possible foundation you can imagine, just on and off. It really makes you wonder, doesn't it? What's next? What amazing future technologies are we all going to build from just these two simple states?